Thank you very much. Hi, my name is Arne Heitmann. I'm a senior system engineer at Mellanox Technologies. As some of you might know, we develop and build our own hardware, and I would like to introduce some probably interesting topics around how does software interact with hardware, or in other terms, how could you get rid of your proprietary operating systems? So a few words about Mellanox itself. Mellanox is a Nasdaq-based organization. We are based out of Yokneam, which is in Israel. All our development is done within Israel, so we are not dependent on the NSA or anyone else. We have a sales headquarters worldwide in Sunnyvale, where the usual suspects are. We are currently around 2,900 employees worldwide. So we are a growing and robust organization. What we do and what we provide is end-to-end products for Ethernet as well as for InfiniBand. Some of you might know the name Mellanox from high-performance computing, from InfiniBand, for example. But since a few years, just around 6 years, we also build dedicated Ethernet products. And our latest Ethernet product portfolio is around our Spectrum switches. And those Spectrum switches, Spectrum-based switches, are the ones I will introduce to you a bit further on, because they provide a lot of openness and a lot of capabilities you might find useful. In addition to that, we also provide Ethernet NICs that could be dual hosted on PCI buses to provide the full speed. We provide 200 gigabit of bandwidth on Ethernet NICs, as well as programmable adapters we also have developed on our own. But now to the original aspect of this speech, which is around decoupling the hardware from the software. The usual aspect and the usual approach you all know from switching technology, from networking technology, is you buy a box, and with that box you buy automatically the vendor's hardware. Well, at least the box vendor's hardware, not necessarily the ASIC vendor's hardware. So we provide and we build our own ASIC, and therefore we have decided to keep it as open as possible. Just like you are used to it from a server, for example. So the typical approach you still buy these days is you buy a switch. The switch has an operating system on it. It's a closed, vendor-locked box. When you think of servers these days, you buy a server. Which operating system do you run on a server? Can anyone name me one? A dedicated one? What runs on a Dell server? Whatever you like, isn't it? Okay, what runs on an IBM server? Whatever you like. What runs on your switch? Whatever the vendor likes. And that's exactly the approach we would like to overcome with our initiative and with our approach of open Ethernet networking. Well, it is a community-driven aspect and a community-driven way to provide an open software for an open hardware. So in other terms, we have, of course, our own operating system. Our own operating system is called Mellanox OS. Like you have Cisco iOS, like you have Arista EOS, like you have Juniper Junos. We have our own operating system. But our boxes are that open that, for example, you can run Cumulus Linux on it if you wish to. Some other organizations also run their own operating systems on our boxes. So therefore, they're completely open. What is the advantage of that? You can run literally any application you want to run. And in terms of routing protocols, BGP or OSPF or ISIS, or if you think in terms of MPLS or Ethernet-based VPN or VXLAN, VTAP functionality, it is nothing else than an application. And I think it is beneficial to really say, well, I want to run my application that is called BERT, because I want to run a BGP on my switch and a BGP on my virtual machines. So therefore, I just run an application, and I program the application in terms of configuring it, like I would do with any other software in the world. One of the first things you need to have is the same you have on each and every server board. you need a bootloader. And the bootloader has to be open. Well, we all know things like bootp, we all know things like netboot and so on and so forth. The open approach for providing a proper bootloader is called ONI. ONI stands for Open Network Install Environment. An Open Network Install Environment works pretty much like a bootb or a PXE boot. In easy terms, it means that you power on your switch. Once the switch boots, it identifies and localizes the ONI bootloader, and the ONI bootloader on the local CPU simply triggers and configures the management network. Once the management network is configured, it can trigger for an operating system and load the operating system from a bootload server. And then you can run literally any network operation system you would like to have on your switch. This all sounds nice, but there are a few more hurdles, of course, to take. But this is one of the first real prerequisites you have to meet. You need a proper bootloader that can interact with diverse network operating systems. Just by the way, once the NOS is downloaded, you simply have to reboot the switch system in terms of loading the operating system. This is just like any other server would do. So how does it work? We know it from servers. Servers have a hardware abstraction layer. The hardware abstraction layer simply builds a solution that is entirely agnostic to the hardware itself. Being agnostic to the hardware itself means just load an operating system, load the necessary drivers, and then you need something like an API that interacts with the CPU or in a networking device with an ASIC. How we do it is a very, very similar approach to any other server in the world. So what we do is we have our user space applications. The user space applications are per se dedicated and defined into 3 different sections. One section is the control plane itself. The control plane itself is the one where all the protocols run between diverse networking devices, for example, between switches or between routers. When you think of a routing protocol, it runs on the control plane. The management plane is everything that runs to the user interface, to the admin interface. So any SNMP trap, for example, runs on the management plane. And the data plane is the thing that some of us wouldn't like to see, because this is where all the problems come in. It is the data that's shifted along the path from end to end. So once this is defined, we need something that abstracts all these 3 planes to the hardware. And this is the so-called abstraction layer. The abstraction layer could be the switch development kit, the software development kit, the SDK. It could be the switch abstraction interface, SAI. Some of you might have heard the term SAI already. It is a term that is fairly related to Microsoft. I will come back to Microsoft in a few seconds again. Or you might have something that is called switchdef. Switchdef is something like an inbox driver, an upstream driver for dedicated operating systems that are open to use this. Once you have this, the next is that you need the low-level drivers. And the low-level drivers are the ones that directly access the ASIC or the CPU. In our term, when we talk about switches, they directly approach the ASIC. They are the one that give the system command that an interface is up, that an interface runs at 10, 25, 100G, that an interface probably blocks traffic because of an access list. This is all done on the switch driving and the system driving level itself. Now some examples. There is a dedicated switch, which is called Sonic. Sonic was shown to the public sometime last year, and Sonic is an open switch system. This open switch system is based on an abstraction interface that is called SAI. The switch abstraction interface simply is something like an API that decouples the software from the hardware. So the software, the network operating system, Sonic, is absolutely open. The switch abstraction interface now translates, more or less, what comes in and hands it over to the API. The API is called Switch SDK, the software development kit. And this now gives all the commands, all the steering, and all the information to the low-level drivers that directly access the hardware. So Psi is open source. Everyone can download it. It's available for free. It is promoted and developed by Microsoft and Dell. It's adopted by the Open Compute project. So you have the first approach of really using your own software with something that decouples everything. Another, even more open way, because I know a lot of people simply don't trust Microsoft. When they hear Microsoft, they think, the evil side of the world. Never trust them. We all like Linux, we like FreeBSD, we like CentOS, we like those operating systems. So why not using a Linux? Using a Linux means you can use any Linux application just with apt-get, download it, or install via an RPM. It's all possible over there. Linux provides a lot of small applications that can do all the networking for you and all the networking functionality. We just have some examples over here. And it's not only the networking, it's also the management plane in terms of automation. When we talk about Puppet, when we talk about Chef, when we talk about Ansible. So use any Linux distribution you would like to have. You would like to have Ubuntu? Well, use Ubuntu. Your Linux admins know Fedora quite well or Debian quite well? Well, if this is your choice, you can use it. So therefore, the only thing you need next is ready to go and developed stable network stack. Well, this is built into Linux anyway. And you need something that it is a sort of a driver. This sort of the driver is the upstream driver, SwitchDev. Just by the way, SwitchDev is available on GitHub. You can directly download it there, and some first Linux applications and Linux distributions already have the first drivers built in. So we have the kernel drivers already built in, and then you just need the switch system underneath. The hardware developers, and this is very important for Mellanox, our DNA is really developing hardware, developing ASICs. And developing ASICs means that we develop our ASICs with APIs that are that open that an upstream driver for the Linux community can easily be used to install your own operating system that runs on a switch. So let's get a bit under the hood, a bit more into the details. So what you see in here, it simply says that the switch itself is treated like a server. It's treated like a server with a lot of NICs. And that's simply it. A switch port is like a NIC. And a 40G switch port that is split into 4 times 10G is like 4 NICs. And that's simply it. It's nothing else than a lot of network interface cards in one single rack unit. Sounds straightforward? Is straightforward. There is no magic behind it. It is a very, very basic approach you see over here. So using this, you need, of course, some traffic control, you need some IP, you need some user space applications, you need your routing daemon, you need your switching daemon, you probably need some access control lists, you probably need some automation in there, you probably need some SNMP and all this. This is all applications running on top of your Linux distribution. And the next step is that this Linux distribution now addresses the low-level drivers, which are called via SwitchDev. The drivers, we call them Mellanox Software Spectrum drivers. The Mellanox Software Spectrum drivers are kernel drivers, so they are upstream, they are inside the Linux distribution. And over there, you just configure with standard Linux tools your switch interfaces. Well, in Linux, it's not called a switch interface, it's called a bridged interface. That's the only difference. But once you look at it, it's called SWP, switch port. But it's called a bridged interface. It's just terminology behind it. Okay? You can build bonds. A bond is nothing else than a link aggregation group on the switch. But as we know now we use server terminology, we call it a bond. We can build tunnel interfaces. We can build dedicated layer 3 interfaces. We can build dedicated layer 3 routing partitions, whatever we like over there. And then the driver simply mirrors these network states and these applications via the Mellanox switch PCI bridge, so via the PCI bus, directly to the ASIC. And this now is a very, very flexible, fast network server. So probably in the future you might not hear the term switch and server, you might hear the term compute server, storage server, network server. Why not? It is all very, very similar. You see over here. Sounds great. I think it is great. It's a very open approach, and it decouples really your hardware from the software. So it really means in the future, you would like to have a dedicated hardware, well, whatever you like. 12 ports, 24 ports, 48 ports, 64 ports. Which operating system would you like to build on it? Whatever you like. Linux, Windows. No. Okay, but Linux probably. Okay, or CentOS. You never know. Whatever comes up. And this is the nice thing. What is available now? The first thing is it all sounds nice. It all is nice. We are in a very, very early phase of it. It's not like buying a switch and directly going into production. You all know this. You're a network operation group. Network operation group also means development. Development of solutions for the future. What you can get right now is you can get a switch that is ready to go for this. The switch that is ready to go for this is called Spectrum. We call this SN2000 series internally because it's a dedicated ASIC build series of switches, ranging from half rack unit to 1 rack unit. Very flexible and cost efficient over there. Once you have a switch, you can get to the next step, and the next step is install your Linux. You can do it via Pixie, you can do it via Oni. If you use Linux, usually Pixie boot is the first option. This is what most of the people know from the server side, so use Pixie boot and install Linux. What you can get already, switchdef evaluation packages. And these switchdef evaluation packages are based on Fedora. They are to be downloaded. You can download them. Of course, when you download them, it is more or less evaluation, it's development, it's working on it. But we are getting there. And it is a community-driven project. So once you have installed it, you probably have to update the kernel version. It really depends. Currently, the development of the drivers is faster than the upstream, okay? And that's very important. But nevertheless, it is an upstream driver. Once you did so, you can run your first traffic. And running the first traffic is build your own layer 2 or your own layer 3 infrastructure and play around with it. Get used to it. See what the benefits are. See that, for example, your virtualized environment for the cloud runs on a dedicated Linux distribution, and you run Quagga, or you run Bird, or you run Snaproot on top of your virtual machines just to advertise their IP address to a root reflector. Well, the root reflector sits on top of the rack, running these applications on the network operating system. And all of a sudden, you have the choice that your virtual machines can just switch wherever they like to switch. The rest is, as usual, just handled by the hardware. So the dirty and rotten traffic path for the data plane still is hardware pure. There is no software involved. So you don't lose something. Just 2 small videos I have. When you can download later on the presentation, you will download it without the videos, because the videos are by themselves just around 200 megs, and this would be a bit too big for an upload or download. But nevertheless, just easy. Over here, an installation of Linux via Pixie. Does not look spectacular, but at least what you see over here is nothing else than a switch. It is one of our Spectrum-based switches, and on the Spectrum-based switches, you see that we have the Pixie boot. It gets the DHCP address, It simply gets the bootloader, you start it, and what you see over here, it installs all the drivers, it installs the operating system. Everything is done just smoothly and automatically, like you know it from any other server in the world. So there is not much of a difference. Once this is done, your switch is ready to be used. Ready to be used means you have an operating system on it. What is needed on the operating system is later on the applications, which is like any other desktop or server operating system. Once you have the operating system on it, you add your applications. So we just wait for the installation to be finished. It's not very spectacular, but at least something happens on the screen. And this is usually my break. You saw Intel over there, which is common because every switch has, for control and for management, a CPU. And the CPU is a normal x86-based CPU that's in there. Now the switch is rebooted. And everything is starting. Next step. Next step is you have to install the application. I have chosen, for demo purposes over here, an application that is well known by most of the people. It is Quagga. Quagga is nothing else but a routing daemon. And the routing daemon is the prerequisite to run a routing protocol, like BGP, like OSPF, like ISIS. So therefore, you need something installed over there. And here you see a sample installation of Quagga. We log in. You see over there on GitHub, we have downloaded all the packages. All the drivers are in there. And now we simply install from the download folder Quagga. And here we are. Quagga is installed. The next, I have 6 other videos, but I don't want to bug you, okay? But the next step would be start the configuration of Quagga, set up the sessions, and all of a sudden, all your traffic flows nice and smoothly through a networking server. So, as mentioned, one of the first steps, get a ready-to-go switch, and the ready-to-go switches are over there. They range from 16 ports of 40G up to 32 ports of 100G. You can run, of course, 25G and 10G. All this is possible on these boxes. So to conclude it, you have a world full of options just in front of you. This world simply says, buy any software. At the moment, we are there, we are open. We invite everyone to also build this sort of hardware. You can use literally whatever you like to abstract this hardware. If you would like to run specific, well, I use the mean word again, Windows-related operating systems, you need another abstraction layer, which is Psi. But you can use, and this is what most of the people do these days, when you use a community-driven approach, you would use switchdev, an inbox driver, and install your own operating system. Currently commercially available is Cumulus Linux. You get everything around this. But if you would like to run, you can run a Fedora testing environment, for example, if you wish to. So any operating system on any switch and any networking related application you can run over there. If you should have any additional questions, just let me know.
Sorry, but I think we don't have any time anymore. Sorry.
I'm just in front or next to this room, so if you have any questions,
Yes,
just ask me.
Thank you very much. Okay, so thank you.